It now gives me the absolute greatest of pleasures to introduce our next speaker, a gentleman that I just met about 30 minutes ago, who I've heard about for an awful long time. Alex Filipenko and I were talking about his history at Mount Wilson in 1981 through about, 83, you said, Alex? 82-ish. 82-ish. He worked here on the 100-inch telescope while he was at Caltech doing his PhD work, and he returns to share with us some of his thoughts about his time here and talk about the future. Thank you, Alex.
Well, it is such a great pleasure to be here and to meet the grandson of George Ellery Hale. I mean, what an amazing accomplishment George Ellery Hale had, actually a series of them consecutively, the 4 largest telescopes in the world, optical telescopes, the Yerkes 40-inch refractor, the 60-inch telescope here at Mount Wilson, the 100-inch Hooker telescope, and finally the 200-inch Hale telescope at Mount Palomar. George Ellery Hale was a real visionary, and it's wonderful to be celebrating the centennial of the Hooker telescope with all of you here today. This is from the website. It's great that this weekend is just a couple of days after November 1st. I know that Dan and a few others were originally thinking of having this be actually Wednesday, in which case I wouldn't have been able to make it because I teach a class of 850 students at Berkeley, and I couldn't schedule the midterm for that day. Instead, I scheduled it for yesterday. And so I was able to come down, and I actually spoke at my alma mater, my undergraduate alma mater, University of California, Santa Barbara, this morning, because they're celebrating the 50th anniversary of a small college that I was a member of within UC Santa Barbara, the College of Creative Studies. So I spoke there this morning, and then I'm looking at Waze, and it's saying I'll get up here in time, and I did get up here in time. So anyway, it is a centennial, and it is a great pleasure to be here. So here it is, the great telescope, and I'm hoping that skies will clear tonight for us to be able to look through it. George Ellery Hale, as I said, led to the construction of the 4 largest telescopes in the world. Very few people at that time had that kind of vision for science, for scientific discovery, for what it would give to humanity. Most people then and now are more tied up with practical applications and stuff. But you know, humans are the only creatures we know of that have the capacity to ask questions, to seek their answers, to build machines with their opposable thumbs with which to seek those answers. And so some subset of humanity should do that. You know, whales and dolphins are pretty smart, but there's no evidence that they ask abstract questions, and they certainly don't build giant machines with which to answer those questions. So I thank Hale and other visionaries for having the foresight to devote their considerable time and effort and funding to the construction of these gigantic machines. An LA Times article came out a few days ago. I think you saw it, or many of you saw it on November 1st. I seem to have lost or forgotten my laser pointer, but you can see there, scientists celebrate 100th birthday of the telescope that revealed the universe, really our place in the universe. And I'm quoted there, in some ways I consider Mount Wilson Observatory to be the most important optical observatory in the history of astronomy. And I really mean it when I said that. Sure, you know, Galileo first used a telescope for celestial studies, which he published, but it wasn't really an observatory. Other people couldn't use the facilities. It was, you know, Galileo's telescope, and he was paid by the Venetian Navy to build these things because they realized they could see approaching enemy ships from afar. So, but there wasn't really a general purpose telescope that other people could use. And Mount Wilson Observatory had a series of these telescopes Oh, thank you very much. Great. With this one right there. Yeah, a series of this. That's a little bit faint, but that's okay. We use red light so as not to mess up our night vision at night, you know. Anyway, this really was a general purpose observatory that many astronomers could use, and I'll tell you why I consider it to be so important. And as it says here, it really was an amazing instrument to use because I used it for part of my doctoral work at Caltech. I conducted observations here in 1981 and 1982. Well, after my undergraduate studies at UC Santa Barbara, I came to Caltech largely because of the allure of the Palomar Observatory at the time. You know, in 1948, the 200-inch was constructed, the Hale telescope, and Mount Wilson Observatory was sort of waning as a research observatory around that time. As a young and up-and-coming astronomer, the 200-inch was the great allure. But though I did have many chances to use that telescope, it's an amazing telescope, the Big Eye, we affectionately called it, I couldn't help but notice from Pasadena all the, radio towers and these telescope domes up there. And of course, as a kid, I had learned about Mount Wilson Observatory and the expansion of the universe. And I thought to myself, well, wouldn't it be fun to actually do a project up at that Mount Wilson, the famed Mount Wilson Observatory? So I asked my advisor at Caltech, Wal Sargent, whether I could put in a proposal to use Mount Wilson, not just the facilities at Palomar Observatory. And he said, sure, go ahead. And one of his other students, who was a year ahead of me, Matt Malkin, who's now a professor at UCLA, he and I got together and proposed a project, which then got accepted, and we used a spectrograph attached to the Hooker telescope. The project was to study the central parts of a certain type of galaxy known as an active galaxy, in particular a Seyfert galaxy, named after Carl Seyfert. So normal galaxies get brighter as you go toward the center because there's just a greater concentration of stars there. That's where gravity pulls them in. But a small fraction of galaxies have a central region that looks extremely bright, and in fact it looks like a superposed star in our own Milky Way galaxy, but a spectrum shows that it's really part of that galaxy. It has the same redshift and so on. So we wanted to study these active galaxies, and it had been speculated that the nucleus of the galaxy shines very brightly because there's a supermassive black hole there, which is swallowing material, and as that material is falling in, but before it has crossed the event horizon, the boundary of the black hole, it glows very brightly because it's releasing gravitational energy. There's an apple, the proverbial Newtonian apple. You can't give a talk about gravity without using the proverbial Newtonian apple, but when things fall, they pick up kinetic energy at the expense of their gravitational potential energy. And if they hit each other or are rubbing against each other, then that bulk energy of motion can be turned into radiation in a quite efficient way. And so even in the 60s, it was decided that supermassive black holes are what power active galaxies. And there's a disk of material around the supermassive black hole, and it emits all kinds of radiation, but basically, the nucleus also has some stars, so Malkin and I wanted to measure the relative contributions of the stellar and non-stellar component to the nucleus of the galaxy. So we came up to Mount Wilson, and here's the monastery, and it brings back fond memories. I just checked in. The last time I stayed at the monastery was 35 years ago, I think, and anyway, it's like a homecoming coming back here. I think I've been here a couple of times to help film some science documentaries, but I'm not sure I stayed at the Mon, as we affectionately called it. Anyway, the monastery is fun. You can look up at the Mount Wilson Institute website some old photographs. This is the living room, library area. Here's the dining room, and the 100-inch observer in the olden days, not in my days, would, I'm pressing on the wrong thing here, would sit at the head of the table and ring this bell whenever the seated astronomers were ready for the next course. And it was called the monastery originally because initially only men were allowed there. There were a few women doing astronomy at the time, and it was really quite discriminatory to not allow them. But as more and more women were grateful that this happened, took on physics and astronomy, times changed. And now there are many, many women doing physics and astronomy, and the monastery is open to all. But it was called the monastery because initially, really, it was mostly men. But there were a few women that unfortunately were excluded, and that's too bad. Okay, well, on that website, you can actually find a relic from the distant past. That relic is a clothespin that has my name on it. And here you can see the description. Yeah, so I was a graduate student. I was not a Hubble or a Sandage or anything like that. The observatory has a memory of all the people who worked there. While visiting the astronomer's dining room, we found a common clothespin that was used as a napkin holder for the newer astronomers. The more established astronomers had wooden rings with their names, proving that current notables, such as Alex Filippenko, had to start somewhere. So I started with a lowly clothespin. I hope it's still there. I asked Maggie, and she didn't seem to know about it, but maybe it's still there somewhere. Is it there, Tom? My clothespin? I want to take a close-up, higher resolution picture of it. What's that? You took that picture, yeah. Anyway, so I want to see my clothespin, and I promise to leave it here as a souvenir for the observatory, and maybe it'll help inspire the younger generation, since I gather from what is said here that I guess I'm a notable now, and so anyway, so maybe I'll help inspire the younger generation the way Hubble and Sandage and Humason and others inspired me, and Walter Adams and Alfred Joy and the many others. Anyway, so there are many wonderful, iconic photographs of the Hooker telescope, and here Hubble is sitting at the Newtonian platform, and there's even been one or two people. I think Alfred Joy fell from the Newtonian platform and broke a bunch of bones, but did not die. You know, it's dangerous to be in darkness in a dome. Now we're all in these comfy observing rooms where, you have your coffee, you don't have to worry about keeping it all in during the night, and stuff. So anyway, but there are many foci, it turns out. There's the prime focus. That's where, when you get up there, you'd better keep it in all night, because it's a giant ordeal to come down, go to the bathroom, and then go back up again. You waste precious time. There's the Newtonian focus, which I just mentioned, the Cassegrain focus, Naismith. And then there's this thing called the Coudet focus, and that allows light to go along the polar axis of the telescope down to a focus which is a very long focal length, basically. This is a way of changing the effective focal length of the telescope. And down there at the Coudet focus, you can spread the light out of a star a lot. You can produce a spectrum that's really spread out a lot. Can't remember whether I included it or not. No, I guess not, but I'll show you some spectra later on. You spread it out a lot. And that's where the spectrograph was that I was using, because to see the signature of stars, we had to look for little tiny absorption lines in the midst of light that was emitted not by stars, not producing absorption lines. And so you have to really spread out the spectrum a lot. So you're down there at the Coudet focus, and it's dark, and it's a cramped location, and you're looking through the eyepiece to make sure that the telescope is tracking the stars correctly. The telescope turns at the rate of rotation of Earth, but the gears have little imperfections and stuff in them, so it's not perfect. You have to guide as well. But it's cramped, and it's dark, and there are many obstacles. But the thing I remember most was that when you would tell the operator to move to a new object, the operator would unlock clamps, and then the telescope could slew to a new object, and then the clamps would lock again. And these gigantic bolts would come out, either in the unlocking or the locking. I frankly don't remember. But it would be a clack, clack. And that first clack warned you, get your head out of there, away from where you were guiding, because this bolt shooting out might hit you. Any of you who work at the Coudet focus, is it still the case that there are these gigantic steel 1-inch thick screws that come out that could puncture a hole through your cranium very easily. So the clack, clack, I remember perhaps more than anything else, because you risked your life. If you worked up here for a long time, you also risked your life because the thing floats on mercury bearings to give it a frictionless environment, or as frictionless as possible. And if you're in there a lot, you're breathing the fumes, and it can basically make you go crazy. And I think 1 or 2 employees of the observatory over its long history did basically go crazy. But I only came up here once in a while, and I don't think I went crazy, at least not yet. So along with the clack clack, you could go down and see the relays. There are all these relays. They're probably still there. I want to go and get pictures of everything tonight. I hope it's clear, but I want to go up there and walk down memory lane. So this is something I found on the internet. I don't even really know who the owner is, so I couldn't attribute it properly. But there are all these relays. Are they still there? I want to see them. You could see sparks flying from the relays and stuff. I mean, this is, 1910s technology, and it's still there. It's just wonderful, Anyway, and I remember going up the long stairs that Sam mentioned several times, and I meant to get here early enough to take a photograph of those stairs and stick it into my talk, but I arrived too late. But I'll see the stairs tonight. Anyway, okay, so we studied these galaxies, and I couldn't find my logbooks. They're somewhere in a box for Mount Wilson Observatory, but I found a logbook for the 60-inch telescope that I used at Palomar, as well as the 200-inch. So here are my logbooks from the Palomar telescope. And then here are actual plots, books with plots of data from the Mount Wilson Hooker telescope. I did find those, and so there you are. Can't quite read it, but these data were probably taken in May of '82 or something like that, and finally around October or something. I think it says 10/08/82 there, so in October I was calibrating the data. So, there's more data. Yep, I found in my office those logbooks. And then here are a couple of published spectra. And what we were looking for were those little tiny dips and stuff. Oh, I do have a laser pointer. Thank you very much. I keep forgetting that. These little dips are from stars. And by measurements of those little dips, there's not much of a dip there. We could tell that most of the light was coming from the gas swirling around this black hole, this region where matter is compressed to such a high density, such a small volume that nothing, not even light, can escape because gravity is so strong. But stuff is swirling in, and that emits light, and that light is non-stellar. So indeed, we were able to separate out the stellar and non-stellar continua of these Seifert galaxies. So here's a paper published in December 1983 by Matt Malkin and myself, based on these data that we obtained at the Hooker telescope in '81 and '82. And I don't know for sure, but I think this was one of the last major papers in the Astrophysical Journal published from data taken at the Hooker telescope before it was closed down, at least for a while. And I must admit, I haven't been following its history very much over the past few decades. I've been associated more with the Lick Observatory and the University of California the past 33 years. But it'd be interesting to look back at the history and see in the early 80s what papers were published from the Hooker telescope then. Of course, in its heyday, lots and lots of papers came out, but telescopes eventually wane. My computer does this once in a while, adjusting the image. I think it's okay. I think all I need to do is just that. No? Back to that. Oh, it is? Yeah, did it do its thing? There we go. Okay, I think now it'll be okay. Yeah, okay. So it'd be interesting to go back and microphone because I know it's being taped. It'd be interesting to go back and see the history of papers and stuff, but I think this is one of the last papers from the Hooker, at least for that era. All right. Okay. So anyway, it was really fun to use, and now let me go back to this statement I made that I consider Mount Wilson Observatory to be the most important optical observatory in the history of astronomy. So why? Well, it's because it revealed our place in the universe. And Sam mentioned the first way in which it did this. First of all, at the 60-inch telescope, what was revealed was that we were not at the center of our galaxy. It was thought that we were at the center of our galaxy. This is the view in the early 20th century, because to the naked eye and to photographs that don't go very deep, that is, that don't see very faint stars, if you look along the Milky Way, you see about the same number of bright stars per unit area in the sky, no matter which direction you look in the Milky Way. Now, with deep photographs, you can actually tell that there are way, way more stars and nebulae and things like that towards Sagittarius and Scorpius, which is where the center of our galaxy is. But with bright stars, it looks about the same all around. And so the so-called Kapteyn universe was one in which we seem to be at the center. It clearly is a disk, because if you look away from the Milky Way, you see relatively few stars. But it looked like we're in the center of the disk. And it's not true, because astronomers at the time did not recognize that there was interstellar gas, and in particular dust, I call it interstellar smog, blocking the view of distant stars. And by the way, I'm very pleased to see, and I occasionally visit Pasadena, go to Caltech, visit colleagues there, but I'm very pleased to see that nowadays the smog in the San Gabriel Valley is far, far less than it was in the late 70s and early 80s. The emission controls really do work, and things like Priuses and stuff. But anyway, so, Okay, but back then they didn't know that there was this interstellar smog. And so it absorbs and scatters light, and so it doesn't allow you to see very far in our galaxy. You only see out a few thousand light years. And we're not that close to the edge of the galaxy, so that looking 3,000 light years out this way takes you out of the galaxy. I mean, we're sort of 2/3 of the way out from the center. It's an ill-defined edge. But the point is, 3,000 light years in any direction gave you about the same number of visible stars, because at greater distances, the stars were simply blocked by all this interstellar smog. It's kind of like the day that I arrived at Caltech. I didn't know that the San Gabriel Mountains were here. I didn't know they were here for a couple of months. I arrived in September of '79. Then after a winter rainstorm, I look up, I go, my goodness, look at this mountain range, okay? So, yeah, smog really does block your view. All right, so this turns out to be wrong. And it was figured out by Harlow Shapley, who was at the time working at Mount Wilson. He later went to Harvard. And what he did with the 60-inch telescope was that he studied the distribution of clusters of stars called globular clusters. They're the most ancient objects in our galaxy. They're about 12 or 13 billion years old. And they're distributed, roughly speaking, in a spherical halo centered on the center of our galaxy. And he couldn't have known that, but he made an educated guess. He noticed that most globular clusters are sort of toward the Sagittarius, Scorpius region, and the general region in that part of the sky, not in the opposite direction. And there were about 100 of these things known, and he figured, well, these objects, these globular clusters, are probably centered on the center of our galaxy. It was a guess. It was an intuitive, it was a gut feeling. And he was right. But the fact that they were off mostly in one direction of the sky, not the other, meant that we were offset from the center of our galaxy. And he could even measure the distances to these clusters by looking at a type of star known as an RR Lyrae star. This is a star that brightens and fades periodically by a factor of 2 or so over half a day. And the true power of these stars was known, and from the observed brightnesses of RR Lyrae stars in the globular clusters, he could derive their distances. Now, he still didn't fully take into account this dust, and so it turns out the RR Lyrae stars looked fainter than expected because dust was blocking some of the light. He didn't know that, so he ascribed their faintness to distance. So he overestimated the size of our galaxy by about a factor of 3, but that's just because, again, they didn't know about the dust. But he correctly deduced that we're not at the center and that the galaxy is a way bigger structure than just 3,000 light years in all directions. It's this gigantic thing, more like 100,000 light years in diameter, and we're out in the boonies somewhere, about 2/3 of the way out. So that was already sort of a extension of the Copernican principle. We're not the center of our solar system, we're not the center of our galaxy. Okay, But now we move to the 100-inch, all right? And with the 100-inch, you go to Wikipedia and you can see some of the main discoveries. You see that in 1923, Edwin Hubble conclusively proves the Andromeda Nebula to be external to the Milky Way galaxy. Whoever has access to fixing Wikipedia, change nebulae to nebula. That should be singular. All right? All right. Well, how did he do that? Well, let's look at it. He basically looked at these spiral nebulae. Originally, that's what they were called. Andromeda was probably the most famous one. This is a more modern picture. Looked kind of like a blur in the sky. And eventually it was realized that there are lots and lots of these things. Now we know with today's great telescopes like the Hubble Space Telescope that there are about 100 billion of them if you didn't have the dust blocking certain directions on our Milky Way. But extrapolated over the whole sky, this picture, which represents a grain of sand held at arm's length, yet has about 2,000 galaxies in it. You know, we could count them. 1, 2, 3, 4. I could spend my hour counting galaxies. That would be pretty boring for you, but it's a rather cushy job. They pay us to sit around and count galaxies. Anyway, there are 2,000, 2,000 or 3,000 galaxies in the Hubble Ultra Deep Field. That's a grain of sand in the sky. It's representative. We've done other ones like this. 100 billion galaxies. So they didn't know about all those spiral nebulae back then, but they knew that there was more than just Andromeda. So if they're internal to our galaxy, that's one thing. But if they're external to our galaxy, that figuratively expands our view of the universe. And that's what Hubble did. Okay? The nature was controversial. In 1920, there was a famous debate, the Shapley-Curtis debate. Curtis said that they're extragalactic. Shapley argued that they're little things like the Orion Nebula in our own galaxy. But they clearly look different. You know, the Orion Nebula is a stellar nursery 1,500 light years away. Some of these things clearly look different. They had a spiral pattern, and I deliberately chose not a modern-day picture of the whirlpool. And plus, they just didn't seem the same. So here's a famous picture of Edwin Hubble with his plate of the Andromeda Nebula, as it was called. And what he noticed was one star here marked with var, a variable star. That's right. And this is a negative photo, so dark things are actually bright. It's a variable star, and it's not just any old variable star. It was a Cepheid variable star. These are related to the RR Lyrae stars that appear in globular clusters, and which, by the way, I studied as an undergraduate project 2 summers when I had a summer job up at Lick Observatory. I photographed a globular cluster called M15 and measured 52 RR Lyrae stars in it. So the Cepheid variables are a more luminous version of the same phenomenon. And they get brighter and fainter, and those that are on average more luminous also have longer periods. So this one has a period of 5.37 days, but they go from 1 day to about 100 days, and the 1-day Cepheids are less luminous than the 100-day Cepheids. And the RR Lyrae stars are even less luminous than them, but they're clearly of the same ilk. So Hubble found a Cepheid variable, and Henrietta Swope had measured a bunch of variables of this sort in the Magellanic Clouds in the south, because Harvard College Observatory had a telescope in the south, and Henrietta Leavitt, though a computer then, she did measurements for the male astronomers of the day, she also wanted to do research of her own, and she realized that there's this period luminosity relationship. Hubble used it. He realized that he's looking at a Cepheid variable that's intrinsically very luminous, yet it appears very, very faint. You can see it here. It's very faint. He correctly deduced that the variable star, and hence the galaxy in which it's, or the nebula in which it's located, must be very far away. And he found other ones as well with which to confirm this conclusion. So that showed that the Andromeda Nebula was very, very far away, because the Cepheids appear very faint, so they must be very distant. By the way, you could say, how do you know they're not faint? Because there's a screen of dust in the way making it faint. If that were the case, then just like dust extinguishes blue light more than red light, and I know you've had your share of fires here. Thank the firefighters that Mount Wilson Observatory is still here. You've all heard about the Napa, Sonoma, Santa Rosa fires that burned 8,500 structures up near where I live. Anyway, the sun, 20 or 30 degrees above the horizon, was a blood red, even in Berkeley a couple of weeks ago. So junk in the air, or interstellar smog, kills off the violet and blue light, the shorter wavelengths, more than the red light. So if interstellar dust were making the Cepheids faint in the Andromeda Nebula, you would have expected them to also appear anomalously red. They did not. Thus, Hubble concluded that they are faint because they're very distant, not because dust is blocking the way. So with this discovery in the Andromeda Nebula, and then a few others shortly thereafter, Hubble figuratively expanded our view of the universe, because suddenly our Milky Way galaxy is just one. And there are others way out there, millions of light years away, and each of them is 100,000 light years in diameter. That was an enormous revelation, absolutely enormous, even bigger conceptually than Shapley showing that we're not in the center of our own galaxy. This was an even more important discovery, okay? And then, I won't have time to talk about this, but Walter Baade showed that there are actually two types of Cepheids, and Hubble didn't know that, so Hubble actually underestimated the distances of the galaxies and stuff. So that was another important contribution. All right. Well, now we move on. Oh, and by the way, Hubble had this tuning fork diagram, right? It's not meant to imply an evolutionary sequence. I think even Hubble did not think it was an evolutionary sequence, but it was a convenient way to classify galaxies, and we still classify galaxies according to their so-called Hubble type. So Hubble was really quite a giant. Okay, next step, Vesto Slipher, not associated with Mount Wilson Observatory, but rather Flagstaff in Arizona. He studied the spiral nebulae a decade before, or 7 years before Hubble proved that they were external galaxies. And he passed their light through a prism producing a spectrum, and these absorption lines tell you what chemical elements exist, et cetera, I won't go into that now, but he noticed that the spectra of these spiral nebulae are basically combinations of spectra of stars, but shifted to longer wavelengths, to the red part of the spectrum, the redshift. Now, a few galaxies don't show this. Andromeda is actually going toward us. It shows a blue shift. That's because it's gravitationally bound to us. We're in a group called the local group. But aside from a few galaxies that are close to our own, almost all the spiral nebulae have these redshifts. But that's as far as Slipher could take things, because he did not know the distances, all right? He just showed that they have redshifts. Hubble in 1929 used measurements of Cepheids to determine the distances of the spiral nebulae, now called island universes or galaxies. I think the term galaxy applied to all of them was by that time in use, because it had been 4 or 5 years since Hubble's discovery that they are external to our galaxy. So you might as well call them galaxies. Anyway, he used the distances to find that redshift is proportional to distance. And that was a very key point, because Slipher did not know the distances, all right? So here's a nearby spiral nebula, M101 in Ursa Major. It's got a redshift, but galaxies in the Virgo cluster, which are smaller looking and fainter because they're farther away, they have a bigger redshift. And you can see that here. Here's again a negative picture of a nearby galaxy. Here's a line due to magnesium, it's called little b. Here are lines due to singly ionized calcium, confusingly called H and K. Not hydrogen and potassium, but singly ionized calcium. I don't even know the history of that. It's the Fraunhofer lines, but anyway, whatever. I do sort of know, but they have a small redshift. Now here's a galaxy that's smaller looking, dimmer, farther away. Same lines, shifted more. And here's one that you see the same lines, and these ones, H and K, instead of being in the violet part of the spectrum, are now in the green part of the spectrum. And the magnesium line, which used to be in the green part, is now in the red part. If this is due to motion, this galaxy is moving away from us at 90,000 kilometers per second. That's nearly a third of the speed of light, 300,000 kilometers per second. Okay, these things are really whizzing away from us. This one 9,000, this one only 900 kilometers per second. So a monumental discovery. And here's an adapted version of Hubble's original plot. There is a line there, but it took a bit of a gut feeling to believe that line, just like, you know, Shapley had to just sort of assume that the globular clusters were centered on our galaxy. By today's standards, this would not be considered compelling evidence, but it was good enough for them. An expanding universe, folks. It became even more compelling, much more compelling, a short time later, when Milton Humason, Hubble's assistant, initially, I believe, a mule driver up the Mount Wilson toll road, bringing up supplies. He sort of worked up the ranks, became Hubble's observing assistant. He and Hubble gathered data that showed that. And Hubble's original data were down there. Wow. Hubble and Humason just 2 years later. Fantastic. Showing pretty clearly the Hubble relationship. At a given time right now, the more distant galaxies are moving away faster than the nearby galaxies. By the way, most of even Hubble and Hubble's data was here within 15 megaparsecs, 15 million times 3 1/4 light years. A parsec is 3 1/4 light years, don't worry about it. But I want to point this out because I'm going to show you a diagram that ignores these 2 points because most of the data were there. Here's a more modern version. The Hubble and Humason plot is in there, most of it. 15 megaparsecs is that little square there. So we've come a long way, baby. In fact, it's gone much farther. We now go out to billions of light years. The 700 megaparsecs is, in fact, 2 billion light years, but in work I'll tell you about if I ever get there. We're not, you know, in a huge hurry, I hope. It's hard to integrate history and my personal experiences and the cutting-edge new stuff, you know. Anyway, we go out to 10 billion light years now, okay? Alan Sandage was Hubble's disciple. He was trained by Hubble. He wanted to take Hubble's law to a greater distance, looking so far away and so far back in time, therefore, that there should be changes to the quantitative Hubble relationship because, you know, the universe doesn't necessarily expand at the same rate at all times. The universe expands because space is expanding. More about that later. I'm getting ahead of myself. Oh, shoot. Well, I'll get to it. But the universe should be slowing down because all the galaxies are pulling on each other. And so Sandage wanted to measure the deceleration, the anticipated deceleration of the universe. Okay? More about that later. But first, I show here the modern view of what the redshift is caused by. Hubble resisted this interpretation for a while. He thought that these redshifts were just indicative or apparent velocities. Perhaps galaxies are zipping through some pre-existing space. The modern view, and it's been verified through observations, and it's consistent with Einstein's general theory of relativity, and Einstein visited here in 1931, so you know it's got to be right, is that the redshift is what's called a cosmological redshift. It's caused by an expansion of space. All right. And when you look at it, all these galaxies are moving away from us. Here we are. And the more distant galaxies are moving faster than the nearby galaxies. Let me pause here for a moment, because there's something very strange about this diagram as I've drawn it. What's strange about it? Yeah, we're at the center. Why would we be at the center? Do all these other galaxies not like us? Is it something we said? Do we smell? Are all these other galaxies lactose intolerant? Get it? Milky Way galaxy, lactose intolerant galaxies. Or when I at Cal tell my introductory astronomy students about cosmology, the study of the structure and evolution of the universe as a whole, as I will starting this coming week, I say, what's the problem? Are we from Stanford or something? With due apologies to those of you who might be Stanford alumni or who have parents or kids who went to Stanford, it's an outstanding institution. It really is. It's just not quite as outstanding as Cal. But anyway, so no, we don't think we're at the center of the universe. In any uniformly expanding universe, no matter which galaxy you're on, you'll see the others moving away. Because if every bit of space expands uniformly, doesn't matter which galaxy you're on, you'll see the others moving away. So we're not in any central, special location. And if you don't like my one-dimensional universe, here's a depiction of an expanding loaf of raisin bread. There's yeast everywhere in the dough. You let it sit around for an hour. Let's say it doubles in size. You're on this raisin. You think, you think you're the center of the universe, but you call your friends and other raisins and they say that they're the center of the universe. The point is there is no unique center of the universe, at least not in dimensions that we can physically probe. There might be in a mathematically describable but physically inaccessible dimension, but that would take me too far afield. By the way, the universe is either infinite or it wraps around itself. I'm not trying to trick you with a finite rubber hose or a finite piece of raisin bread. Okay, so what's expanding? You know, people often glibly say, the universe is expanding, everything's expanding. Well, that's not quite true. You're not expanding. Well, you might expand after a big meal, but that's your fault, not the universe's fault. Electromagnetic forces hold you together and resist the tendency of empty space to expand. Earth isn't expanding. It's held together by gravity, which completely overwhelms any tendency of space to expand. Our solar system is not expanding. It's held together by the sun's gravity. Our galaxy and the Andromeda Galaxy and other galaxies are not expanding. They're held together by the gravity of all the stars. Even clusters of galaxies are not expanding. Now, we're out to a few million light years in size now, and yet still nothing's expanding. So what do you mean the universe is expanding? At distances beyond a few million light years, where you have either isolated galaxies very far apart from each other, or clusters of galaxies that are far apart from each other. Say, on scales of 10 million light years and beyond, to be safe. That's where the universe is expanding. 10 million light years and beyond, to within the nearest order of magnitude. Okay. Well, you can extrapolate this expansion backward in time. The universe used to be denser and hotter. It's just like expanding gases cool. When you compress a gas, it heats. So the compressed, dense universe should have been hot, could have begun in a single dense, very hot state. We call that beginning the Big Bang. Fred Hoyle actually used the term kind of derisively. He thought it was a joke, this Big Bang expansion, this birth of the universe. Many astronomers have said that we really need a better name for the birth of the universe. So various astronomy magazines, Sky and Telescope and Astronomy Magazine, occasionally hold contests for people to think of a replacement for the Big Bang. A suitable candidate has never risen high enough to replace that term, but one of my favorites is Bertha D. Universe. Okay? Let's call the Big Bang the Bertha D. Universe. Okay. All right. So there it is, the Big Bang. Stuff comes out. From where, we don't know. People are studying that now. There are all these ideas on inflation and stuff. Take my course. I have this course with the teaching company, the great courses. Several of you have said you've listened to all 96 of my lectures. My goodness, you deserve a prize, okay? But anyway, I describe all this stuff more there. So it's expanding, all right? But you know what? The matter in the universe should slow the expansion down. And moreover, also done here at Mount Wilson, Fritz Swinky finds evidence of dark matter. So here's the story behind dark matter. Fritz Swinky, a professor at Caltech, one of my heroes. He died before I arrived. Is Channon Price still here? Channon, was he still? You were an undergrad at Caltech. Pardon? He was still alive? Yeah. Did you know him, Channon? Yeah. You saw him. Anyway, he was a brilliant man, decades ahead of his time in many ways, He had some crazy ideas, but a lot of really great ideas too. And often the mark of a good theorist is just have lots of ideas. Some will end up being wrong. That's okay. As long as he didn't add 2 and 2 and get 5, it's okay to get the wrong answer for reasons that are subtle. But he wasn't well liked among the Caltech astronomers. My advisor, Wal Sargent, was one of the people who got along with him. He wasn't well liked because he was arrogant and abrasive, and he didn't think much of the intellectual capabilities of his Caltech colleagues. Now, Caltech is a pretty brainy place. There are not that many dumb people at Caltech, and his colleagues, and none among the faculty, okay, and his colleagues did not react well to him thinking that they're intellectual lightweights. Here, perhaps he's showing you what he thinks of the typical brain size of his colleagues. Now, I don't know that that's what he's thinking, but he might be thinking that, and he's on record for having referred to his colleagues as spherical bastards, because, they're bastards any way you look at them. Now, a sphere is the only geometric object that looks the same from all directions. I do not necessarily suggest you start calling your friends and neighbors spherical bastards. You will end up friendless. But anyway, I also think there was some intellectual jealousy there. A few of his colleagues probably thought that he really was smarter, and that bummed them out. But anyway, he observed some clusters of galaxies, in particular the Coma cluster of galaxies, and he knew that there are many clusters. And he measured the speeds of galaxies in the Coma cluster. And he said that the Coma cluster would fly apart unless there's extra gravity, more than what is associated with the visible stars and galaxies. That was one of his proposed solutions. He didn't make a big deal out of it. He had other possible solutions as well, but in his paper, he refers to dark matter. One possible solution is that there's dark matter that holds the Coma cluster together, and we just don't see it. And indeed, other clusters must be held together as well. They're not just chance galaxies passing through the night. There are way too many clusters for them to be just a chance superposition of galaxies. So he did not make a big deal of it, but he did come up with the idea of dark matter. He was ignored. This is the early 30s. Yeah, I just love that picture. His descendants don't like that picture, but it's in the archives and it's in the public domain, I think. So anyway, decades later, Vera Rubin, who passed away just last Christmas, actually, at the Carnegie Institution of Washington, all right, studied spiral galaxies and found that they're rotating so quickly that they would fly apart unless there's extra gravity associated with material that's there but does not shine. So this is now mid-70s, Zwicky mid-30s. People thought that Vera Rubin has an incorrect result as well, just as they thought that Zwicky has an incorrect result. But it gradually caught on because other people started making similar observations. In my opinion, actually, Rubin deserved a Nobel Prize for her work, and she never got it. I really think that was unfair. So there's dark matter in galaxies, there's dark matter in clusters of galaxies, there's lots of additional evidence for it now. Some of you will see that there are all these arcs and stuff. These are background galaxies being gravitationally lensed by not only the visible matter, but the dark matter in this intervening cluster of galaxies. And there's lots of other evidence for dark matter, and 90%, actually 85% of the gravitating stuff in clusters of galaxies is dark. The visible stuff is a minor component. What is dark matter? Well, we still don't know. We think that it might be WIMPs, weakly interacting massive particles. They might be machos, massive compact halo objects. The WIMPs have been winning, but lately, with the detection of gravitational waves from merging binary black holes, the possibility that machos, massive things, is on the rise, I would say. And also, physicists are looking for WIMPs and still have not found them. That does not kill them, in my opinion, yet, but their stock is going down and possibly machos are going up. All right, well, back to this. We know the expansion rate. I'm going to accelerate here a little bit. We know that from various observatories, and it's whatever number it is. I'll tell you more about it later. But it should be changing. And this is where I was a little bit off. That's because I finished preparing this talk at 4 in the morning last night. Because I knew I'd be driving from Santa Barbara to here, and I can't work on my talk while I'm driving, so I had to finish it last night. All right. So Newton, right, says gravity pulls. So all the galaxies should be pulling on one another, not just because of the visible matter, but the dark matter as well. And the question then is, how much is the universe decelerating? And that was the question that Sandage set out to answer after confirming even better Hubble and Humasson's result for just simply the expanding universe. He wanted to see changes in the expansion rate. And he wrote a famous paper where he essentially said that with the Palomar Hale telescope, they should be able to solve this problem, because the Hale telescope, a bigger telescope in a darker location, Los Angeles was beginning to blossom by the 60s, more than beginning, you know. So he said, with the Palomar 200-inch, we should be able to look far enough away, look far enough back in time to see changes in the Hubble relationship. So he started this whole journey, and the basic idea is that if the universe is dense, then galaxies will be slowing down, receding away from you, looking smaller and fainter. You'd say, I live in a well-behaved, nice universe, but then you might notice something strange. Here you'd get kind of nervous, and then, goodbye, cruel world, because if there's enough matter, there we go, then the universe will eventually stop and then recollapse. However, had I eaten my Wheaties this morning, and if there weren't the technical difficulty of this ceiling, I could, in principle, heave this apple at a speed greater than the escape speed, and though it would be slowing down forever, you can't stop gravity, it would not come to a stop, and most definitely wouldn't come back down. It might come to a stop at infinity. That's exactly equal to the escape velocity. Or I could throw it faster. So if the density of the universe is low, then the expansion will decelerate forever, approaching some constant speed as time approaches infinity. But that universe would become cold and dark and dilute, a very different fate from the Big Crunch. By the way, you could say Big Bang, Big Crunch, or you could say Big Bang, Gnab Gib, which is Big Bang backwards. Okay, so how do you figure it out? Well, you measure the history of the expansion. Just like if I were to measure the speed of this apple at many different times, I could see how much it's been slowing down. I could then figure out whether it'll stop or not. Simple physics, okay? If it's not been slowing down a lot, then it'll keep going forever. So we know the current expansion rate. Let's look far enough in time that we can measure changes. So light travels at a finite speed. You see the sun about 8 1/3 minutes after light left it. That's how long it takes to traverse 150 million kilometers. The typical bright stars you see in the sky are some tens or hundreds of light years away, so you're seeing them as they were tens or hundreds of years ago. Galaxies might be 1 billion light years away, or 4 billion light years away, and maybe that little smudge there is 9 billion light years away. You're seeing them as they were 1, 4, 9 billion years ago, and encoded in the light, in the form of the redshift, is how much space has expanded during the time that the light was on its way to you. So if you know how far back in time you're looking, and you measure the redshift, and you do that for a bunch of different galaxies at different look-back times, you essentially measure the expansion history of the universe. That's the idea. The finite speed of light gives us a movie of the history of the universe. Well, nearby galaxies, you figure out their distances by, Hubble's method. Find a Cepheid variable, or, let's call that star Sam, and let's say that star is just like Betelgeuse, the left shoulder of Orion, a luminous, powerful star. And you say, Sam is exactly the same kind of star, you can tell from the spectrum. To look that faint, Sam has to be far away. All right, and then you do this for other stars, Edwin and Milton and others, and if you get the same answer, that gives you confidence that you're getting the distance of the galaxy. That's essentially Hubble's technique when he first identified that the spiral nebulae are external galaxies. You do this all the time when you judge the distance of an oncoming car. You've calibrated the brightness of the headlights of a car of known distance, like 6 feet away from you, and then you look at the headlights of more distant cars. They look fainter. You almost intuitively, almost instinctively determine their distance. If you're not very good at doing this, you shouldn't be driving at night. Okay? So cars, stars, it's the same thing. But you might say those Cepheid variables are seen reasonably easily in relatively nearby galaxies. When you look at galaxies that are perhaps 4 billion light years away, you don't see any individual stars. Even very luminous stars like Cepheids, which can be 10,000 times as luminous as the sun. That's nowhere near enough to be seen from distances of billions of light years. So it sounds like you're hosed, but you're not. There is a type of star that's brilliant enough to be seen from distances of billions of light years. Anyone know what it is? A supernova. That's right. An exploding star can become several billion suns. All right? And sunblock of 50 wouldn't cut it, folks. If our sun were to do this, you'd need sunblock or supernova block of a few billion to protect yourself. All right? But don't worry, be happy, our sun won't do this. But studying stars that do this is very exciting and helps us understand our origins. Because stars generate the light that they emit by fusing light elements into heavy elements. Our sun is producing helium from hydrogen right now. Later it'll produce carbon and oxygen. But if all stars were like our sun, and that carbon and oxygen and other elements remained forever trapped deep inside the core of the star, then it would never be made available for the production of new stars, planets, and life. But some stars do blow up, and they eject those heavy elements and create new ones during the explosions. And those chemically enriched gases go flying out, and we measure the chemical composition of things like the Crab Nebula. That's 1,000 years old. After tens of thousands of years, the gases spread out even more. Then they join with other gases and form gravitationally bound, unstable systems like the Orion Nebula from these chemically enriched gases. And the trapezium lights up the Orion Nebula. But if you look, especially at infrared wavelengths at the Orion Nebula, you see stars that are still forming or are newly formed, and they have disks of debris around them, dust, fine little particles formed from those heavy elements. And somehow, somewhere, 4.5 billion years ago, in our own solar system, terrestrial planets formed, and then life formed. We don't know how that happened. I'll leave that to the biologists. The things they deal with are far harder than anything we deal with in astrophysics. Life evolved. I'm skipping a few steps here. Finally resulting in Homo sapiens, who have the intellectual capacity and the curiosity to ask questions and attempt to answer them. And they have the thumb with which to build machines, to figure out where did the elements in their bodies come from? Where did the elements in their DNA come from? And here's my DNA, some of my DNA. I happen to have 4 children. So anyway, it's fantastic. So we find these exploding stars. And it would be I would be a really cruel advisor if I were to make each of my students look at one and only one galaxy in search of a supernova, because in a galaxy like this, a supernova might go off every 30 or 40 years. If I make a student do that, I will have had decades worth of labor before we let them graduate and move on to greener pastures. Yeah. There are some crimes that are so egregious that even a tenured professor can and should get fired. That would be one such crime. However, it's a statistical process. You know, if there's a supernova per galaxy per 100 years, let's say, just for simple numbers, then there will be a supernova per year per 100 galaxies. On average, one of those galaxies will produce a supernova in any given year. All right? But it would be still kind of cruel if I were to look or make my students look at hundreds or thousands of galaxies, finding some supernovae, and then we let them graduate. It's much easier with electronic cameras, like the ones, your digital cameras, though we use CCDs instead of the typical CMOS devices that most of your cameras use. We attach them to the eyepiece end of a telescope, take photographs of thousands of galaxies, and then we simply look for arrows. And where you see an arrow, you see an exploding star. See once, twice, 3 times, 4 times, 5 times. By rigorous mathematical induction, I conclude that this procedure works every time. Well, it can't be that simple. The Swinky looked for supernovae, and he didn't have any arrows pointing to guide him. What we've developed actually at Lick Observatory is a robotic telescope, small by today's standards, small even compared to the Hooker telescope, small even compared to the 60-inch, 1.5-meter telescope. But it's automated. It's been programmed to take photographs of thousands of galaxies per week, and then it repeats the process. My associate Wei-Dong Lee programmed it, and here you can see before and after pictures of one galaxy. This is a special case where there was something new in the picture right there. Not the arrow. We put that in with Photoshop. So that could be a supernova. It's a supernova candidate. Could be some asteroid that's flying through the field of view with Earth's name written on it. Someday astronomers will find that asteroid, and clever physicists and engineers will figure out a way to deflect it. So support your local astronomer. He or she might help save humanity someday. But one person's gold is another person's garbage. My team is not interested in the asteroids. So I have a group of students who look at the 12 or so candidates each night out of 1,000 images, determine which ones are likely to be genuine exploding stars worthy of follow-up observations. And these undergraduates get really jazzed up by doing research, real research, and helping find supernovae. They don't always go on to become professors of astrophysics, but they're more likely to go on in fields of science and technology. I say that astronomy is that gateway science. It's the bug that bites kids, most of whom won't become astronomers, but who are more likely to pursue science and technology, and it gives research experience for undergraduates. Okay, well, having found a supernova, we then use a bigger telescope to collect more light, get a spectrum. These things come in several different varieties. Let me just mention that for the ones that are used for cosmology, those are the type 1As. I'm going to accelerate a little bit. We've measured type 1As in galaxies whose distance we know because we've found Cepheids and stuff in it. So we calibrate the headlight with this supernova, and we do that with a bunch of them because they might be different. We then try to find distant ones, okay? Because measuring the apparent brightness will tell the distance and hence the look-back time, and measuring the spectrum will tell the redshift, how much space has stretched, okay? So, my colleagues on two teams, and I was the only person actually who was a member of both of the teams that did this work. My colleagues used big telescopes, primarily in Chile, to take wide-angle pictures of the sky, pictures as wide as the full moon. And in these pictures are mostly galaxies. Very few stars in our own galaxy in this picture. You look deep enough, the universe is mostly galaxies. So there's a few thousand galaxies there. You repeat that picture 3 weeks later. You subtract the older picture from the newer picture. Here's a subset. And there's something that looks like it might be interesting. That's a supernova candidate. My job on both teams was to take a spectrum to make sure it was a supernova, and in particular a type 1A supernova. I knew I'd be running out of time, so I cut that part out. I have access to currently the world's greatest telescopes, the 400-inch or 10-meter Keck telescopes, owned and operated by Caltech and the University of California. I feel very privileged to be able to use those telescopes. And we're now planning a 30-meter telescope, hopefully to be placed in Hawaii, but there are political issues with Hawaii, so it might end up being built on the Canary Islands. But I've been just blessed to be able to use these, in progression, the biggest telescopes in the world. I couldn't have dreamed this as a kid. So I would take spectra of the candidates with these gigantic pieces of glass. Now, multiple pieces, because you physically can't make a piece of glass that's single, 10 meters in diameter, or at least it's cheaper to do it with a bunch. There's Fred Chaffee, a former director. You think the Hooker is big. It is, at 2.5 meters. This is 10 meters. These are becoming truly gigantic telescopes now. The legacy of Hale, really, right? So here's a spectrum of one of our candidates, and the spectrum has bumps and wiggles that look a lot like the spectrum of a nearby type 1A supernova. When we got data like this, I was a very happy camper. And now you see the real reason we build observatories in Hawaii. The San Francisco Bay Area water is too cold for swimming. It's not like LA. I don't like putting on a wetsuit, so I like going to Hawaii. But there are good scientific reasons for building in Hawaii as well. The punchline is this: the supernovae were really, really faint. And you might say, well, okay, they're in these pathetic, scrawny-looking galaxies here. You can't even see the galaxy. Obviously, these galaxies are very distant. Obviously, the supernovae should look very faint. That's true, but they looked fainter than expected. Here's the deal, okay? If I toss an apple up, let's say the universe is just 1 second old. It goes some distance, I can measure that. But it's been decelerating. If Earth's mass were less, the gravity would be weaker, and so it wouldn't decelerate as much. Now, I can't make Earth's mass less, but I can do the next best thing. I could throw it faster, and in 1 second it goes higher. If there weren't any gravity whatsoever, then there'd be no deceleration, so it would get even farther in 1 second, right? But that's the best you can do in 1 second. You can't go farther than at a constant speed unless something speeds up the object, right? If there are rockets attached to the apple, then you could go zoom, and you could go a greater distance than what you would achieve at a constant speed. We found the apples, the supernovae, the galaxies in which they're located, to be fainter, to be more distant than they should have been. And it turns out the exact argument is independent of whether I assume the universe is 1 second old or 2 seconds old. They were more distant than anticipated based on their redshift. That's for the aficionados, that's what we found. And the eureka moment came to a postdoctoral scholar of mine, Adam Rees, whose notebook is shown here. He was measuring the density of the universe using a unit called omega, and it should have been positive, and he got a negative value. That means not deceleration, as would have been caused by attractive gravity, but acceleration as caused by anti-gravity. Bizarre. Well, I was fortunate to be able to announce this result first at a meeting in LA, here in Marina del Mar, for Brian Schmidt's team and for Adam Rees, my postdoctoral scholar whose work I was supervising at the time. Astronomers see a cosmic anti-gravity force at work. We use that term anti-gravity hesitantly because people ask us, can we attach this stuff, whatever it is, to our cars and levitate over LA traffic jams? And the answer is no. You cannot attach it to your car. It's either a property of space that cannot be harnessed at all, or there's so little of it that it can't possibly be harnessed. Well, the published papers talked about this. The papers published in September of 98 and June of 99. By the end of 98, the editors of Science magazine said that this was the most important discovery that year in any science, because it pointed to anti-gravity, and the legacy of Hale and Hubble and Sandage was an accelerating universe rather than a decelerating universe. This is bizarre. The character of Einstein looks surprised here, not because he's blowing multiple universes out of his pipe. You might not have known that there are multiple universes and that they come from the pipes of theoretical physicists. Well, the first part of that statement might be true. There might be multiple universes. But he had postulated an anti-gravity effect in 1917 because he and other physicists, by and large, thought that the universe was static, neither expanding nor collapsing. Hubble had not yet made his 1929 discovery. This is 1917. So Einstein proposed a repulsive effect that would negate the attractive gravity, giving a static universe. The net force would be zero, right? The Star Wars movie is coming out soon. May the force be with you? No. May the net force be with you. The force may be with you, but if some force is against you, you're going to lose. May the net force be with you. Here, the net force would be zero. The universe would be static. Well, he renounced his idea and felt sad about it 12 years later when Hubble discovered that the universe is expanding. It's not static after all. The whole physical and philosophical motivation for the cosmological constant vanished. Einstein could have been famous if he had predicted that the universe is in a dynamic state, but he didn't. So here he's sad. And I don't know that that's what he's thinking, but he might be thinking that, right? What have we done the better part of a century later? We've rejuvenated the idea of a repulsive anti-gravity, not to give a static universe, but one which over the biggest distances, 10 million light years or more, is accelerating. And if if Einstein were around right now to see our data and other data, his reaction might be something like on the cover of Science magazine. Well, very briefly, there's a lot of evidence for this stuff now. We don't know that it's the cosmological constant. It might be something else. We call it more generically dark energy. It might be the vacuum energy of space, in which case it's the cosmological constant, but it might be some new energy field, a little bit like electromagnetic waves are passing through this room, but that's, whatever it is, it's not an electromagnetic wave. It's important because when you sum it all up, it's 70% of the contents of the universe. And we don't know what it is. Dark matter is 25%. We're not really sure what that is. The universe with which I grew up as an undergraduate was this. That was the whole pie back in the 1970s. Yeah, there was some evidence for dark matter, but most of this 5% is not easily visible anyway. Only 0.5% is. So, okay, let that be what we call now normal dark matter. But that was the universe in the 1970s. Here we are 40 years later, and this is the universe. And 95% of it is still not understood. We just know it's there. So given the importance to this, probably the most important observationally motivated problem in physics, what is the nature of dark energy? 70% of the universe. Probably a quantum phenomenon that applies to the whole universe, and thus a possible clue to quantum theories of gravity. By 2011, it had been established enough through independent measurements and agreed to be so important that it was honored with the 2011 Nobel Prize in Physics. The rules of the Nobel state that it can go to only 3 people at most. Saul Perlmutter, the head of one team at Berkeley, Brian Schmidt in Australia, and my postdoc, Adam Rees, who was working with me on Schmidt's team. They were the chosen ones, but they understood that without the rest of us working in the trenches, they wouldn't have been honored in this way, so they spent a good fraction of their prize money flying the rest of us out to participate in Nobel Week in Stockholm in 2011. There's the ceremony. Right after the ceremony, there are Adam and Brian. Saul's group picture is here. I'm not in that picture, despite being the one person who was on both teams. If you get me sufficiently drunk some night, I'll tell you about the politics of that. But anyway, yes. So it was a nearly independent set of teams, but anyway. I'm not in that picture because at that very moment, my primary team, Schmidt's team, was having its celebratory lunch. And at that lunch, my wife Noelle revealed her consolation prize to all of us who did not technically win the Nobel Prize. And it was Dark Energy is the New Black, a t-shirt. By the way, there's no shame in not winning the Nobel Prize. Hubble never won the Nobel Prize for his discovery of the expansion of the universe. Anyway, my wife sent this and a $2 bill to the King of Sweden saying, here are 2 items you are unlikely to already have. But anyway, just a couple of years ago, the Breakthrough Committee, which honors all participants in a discovery, honored this discovery. They understand that unlike the days of Alfred Nobel, science is now a very collaborative process. It's very few cases where a lone, rugged individual is doing all the work, him or herself. So they acknowledged all the members. But it wasn't really the prizes that are important. It was participating in a revolutionary discovery. You know, as a kid, I never thought I'd be involved in such an important discovery. And really, the legacy of Hale and Hubble and Sandage and Humason, an accelerating universe. Truly bizarre. So how will the universe end? Well, if the acceleration continues and you want to look at a galaxy with your very own eyes, you'd better come up to Mount Wilson on a clear night sometime soon, because within a few tens of billions of years, all the galaxies will have been whisked away, and they won't be visible anymore. But is dark energy really the cosmological constant? Will the acceleration continue? We don't know. The data are consistent with the cosmological constant, but we're still not sure. It's possible still that the dark energy will gravitationally change sign someday in the future, in which case it's still possible that there would be the big crunch. It's also possible that it'll get stronger and we will all get ripped apart someday. That's the big rip or the big rip-off. So we're now trying to measure the past history even better in order to predict the future. And the most recent surprise, I know I'm way out over time, but there's no next speaker, so what the hell. There was this morning in Santa Barbara, and then we'll let people make a graceful exit and we'll do some questions. But I thought there's one keynote and 100 years celebration of the Hooker telescope. You'll forgive me? Okay. All right. The most recent surprise. The current rate of expansion is faster than expected, even when you take into account all the stuff that I just talked about. In what way? Well, here's the point. There are exquisite measurements by radio astronomers that measure the afterglow of the Big Bang, the cosmic microwave background radiation. They're essentially taking a picture of the universe when it was only 380,000 years old. That radiation now corresponds to a temperature of only 3 degrees. We live in a much warmer place because this is not typical. We're near a star. But the universe is 3 degrees, and there are little fluctuations in temperature. Long story short, from the observed fluctuations back when the universe was 380,000 years old, and from an extrapolation based on this cosmic pie, based on the assumption that the dark energy is the cosmological constant or something very close to it, they can predict the current Hubble constant. Okay? So by measuring the universe when it was very young and by extrapolating based on what we think we know, they come up with a predicted value. All right? Well, all right. The latest and greatest such measurements are with the Planck satellite. They come up with 66.53 with just a remarkably small error bar, plus or minus 0.62 kilometers per second per megaparsec. You need that inverse distance there because obviously the more distant the galaxy, the greater is the amount of space. So the expansion rate, if it were just kilometers per second, would depend on the distance you're talking about. That's why there's that per megaparsec thing there. Don't worry about the units too much. Just look at that number, okay? Previous direct measurements had been of the current expansion rate, 70 to 75. And by the way, I forgot to mention it, but Hubble's disciple Sandage came up with a value of 50, and he had big fights, in particular with an astronomer at the University of Texas, Gerard de Vaucouleurs, who thought it was closer to 100. So the big fight was factor of 2, 50 or 100. That sets the scale of the universe. We've done pretty well with the Hubble Space Telescope and others, and we've narrowed it down to here. But it's still a pretty big error bar. And with this error bar, a number in here is formally consistent with that. So no big deal. But, possible conflict, but error bars overlap quite a lot. Okay, so what have we done? We've used the Hubble Space Telescope, and this is a project run by my former postdoc Adam Rees, now Nobel laureate. We measured accurately the distances of about 20 nearby galaxies in which type 1a supernovae had occurred. And we did this by using Cepheids. So we found a whole bunch of Cepheids, and we made measurements of the galaxies, and we got really good distances. This is the computer telling me I really need to stop, and I will in about 3 minutes. Okay? So now it'll reappear. So there it is, adjusting the image. So we measured the distances really accurately, and we played with the error bars. We think we really understand them. So our current latest and greatest expansion rate measurement is 73.24 plus or minus 1.7. Okay, the Planck measurement was 66.53 plus or minus 0.62. For those of you who know statistics, this is a discrepancy at about the 3 standard deviation level. Not super compelling, but when we first announced the accelerating expansion of the universe, that was only a 2.5 to 3 sigma result, and we turned out to be right, So, we published this, and we said, here's our data, here are our measurements, here are the things that might be going wrong, but we haven't found anything obviously wrong. So there appears to be a conflict. I won't bet my life on it, I won't bet my house on it. My wife would be upset if I even bet our cat on it. So I'm not going to bet my cat on it, because she might watch a recording of this talk someday. But there might be a conflict. We have smaller uncertainties than before, and we think we really understand them. All right. So maybe we're wrong. Maybe the microwave measurements are wrong. That's possible. But, okay, that's sort of boring. So let's, for the time being, suppose both teams are right. Here are the possible things in order, in my opinion, of increasing probability. General relativity is wrong. I think that's unlikely, especially now that gravitational waves have been detected from merging black holes and even merging neutron stars. And relativity is just so beautiful. It may be wrong at the quantum level. We know it's incomplete at the quantum level, but on big scales, I just don't think general relativity is wrong. But it might be. Dark matter may be behaving weirdly. Shouldn't interact with light, but it might in some weird way, causing a problem in either one of the measurements. Dark energy might be becoming stronger. If that's the case, then it's not the cosmological constant, and someday even we will be ripped apart. I don't think this is the case because there's a lot of other evidence showing that it's either the cosmological constant, or if it's not a constant, it's changing very little, not enough to explain our results. So I don't think this is the answer either. So then maybe there's a new very light subatomic particle that hasn't been included in the particle physicists' dictionary yet, in a sense, or at least in their census. There are such hypothetical particles in their dictionary, but they didn't think they exist. A possible type of neutrino, a thing called a sterile neutrino, or some other weird thing. We call it dark radiation generically because we don't know what it is. But if it exists, it would alter, it would affect the early expansion rate so that the extrapolation to now would be wrong. Because if not all the ingredients are taken into account, you'll get a wrong answer if you take the early time measurements and the standard model, because the standard model doesn't include this ingredient. So that would be really exciting. It would be yet another new case of astrophysical measurements leading to a revolution in particle physics. This would be really, really neat. But I'm not saying that this is the solution at this point. I'm just saying it might be. I'm hoping that the result stands and it's not an error on our part or the other team's part. And if it stands, then we're going to have to explain it someday, and maybe this is the answer. So we don't know. Stay tuned. That's for the future, and that too will be a legacy of the Mount Wilson Observatory. So I wanted to acknowledge generous support from many, many institutions. It's fantastic that this place was built. The 60-inch telescope, the 100-inch telescope. It's hard to believe it's been a century since the 100-inch was built. But I hope to have given you a flavor both of the early history, my early involvement as a graduate student, and where all this led in the ever-expanding tale, if you'll pardon the pun, of the study of the expansion of the universe that was discovered right here with the Hooker telescope at Mount Wilson Observatory. Thank you very much for your attention. You're too nice to me. Those who want to make a graceful exit, I know it's nearly 6 o'clock. Go ahead and do so. For the others, Dan and others, is there time for some questions? Yeah, great, wonderful. I'll repeat the questions for the benefit of others. So let's get started even while people are leaving. Yes?
Okay, so there's antimatter and there's matter.
There's antimatter and there's matter. Yeah.
So the question is, when did this cancellation that left what's
Right.
left happen?
So the point is there's matter and there's antimatter, but we haven't found any galaxies made out of antimatter, so there's clearly an imbalance. How big is it and when did it occur? It's only about a part per billion. In other words, for every billion protons, for every billion antiprotons early in the universe, there was 1,000,000,001 protons. So only that one couldn't find a partner. And that happened well before the universe was 1 second old. All right? Probably about a millionth of a second after the Big Bang or even earlier. And we don't know how that occurred. Physicists have found parity-violating reactions, the decay of the neutral kaon. Val Fitch and Jim Cronin win the Nobel Prize for that. That's a parity-violating reaction, but that's not the reaction that gave rise to the baryon asymmetry early in the universe. We actually don't know what reaction gave rise to that asymmetry, but we know it can occur. Let me take some other questions, then we can follow up. But I want to give people a chance to ask one question. Yes?
If you could get one additional tool to help astronomical research in general.
Yeah, if I could have one additional tool to help astronomy research in general, what would it be? So it just happened. I would have said for most of my career, gravitational waves, because those are not electromagnetic radiation. Those are a change in the actual lengths between objects. You know, there are changes in lengths of space-time and changes in time as well. They provide information that's completely different from what electromagnetic waves provide. And in September of 2015, just 2 years ago, they were detected in part by physicists at Caltech and MIT, LIGO. And the Nobel Prize in Physics this year went to the leaders of those two groups, the MIT and the Caltech groups. Ray Weiss at MIT, Kip Thorne and Barry Barish at Caltech. And very sadly, Ron Drever should have won it as well. I'm not saying anything negative about Barry Barish, but in the ranking of people and importance, well, it's hard to say. That's why the Nobels are unfair. It wouldn't have gotten done without Barry Barish, but it wouldn't have gotten done without the very hard work of hundreds, even 1,000 people. So how do you rank them all? But anyway, it went to Kip Thorne, Barry Barish, and Ray Weiss this year. So we now have gravitational waves. That's fantastic. So now that we have gravitational waves, what will be my new choice? I'm not sure. I need to think about that question. What would be my new... yeah. An all-purpose telescope that sees it all. I'm not sure. Let me think about that. I mean, for years I've been answering that question with my stock answer, gravitational waves. But in the past 2 years, no one has asked me that question until you asked me that question. So now I need to think about my answer again. Another question there. I thought I saw some hands up. Don't be shy. Yes, right there. I'm sorry? How do you calculate energy in an accelerating universe? Okay, that's a very deep question, it turns out. And it has to do with the early inflationary era of our universe when it went through an epoch of exponential expansion. How did you get something out of nothing? It seems like it's not conserving energy. Similarly with this dark energy, the cosmological constant being an energy in an ever-expanding universe, we've got more and more dark energy. Sounds like we're violating conservation of energy. I'll give you the brief answer, in part because even relativists sometimes argue about this. But it turns out that energy is conserved in a way where the following analogy is useful. If I drop this apple, it gains energy of motion, kinetic energy, 1, 2, 3, 4, 5 units of kinetic energy. Looks like I've created something out of nothing, but I haven't, because I had to do work on this apple to lift it up. I gave it potential energy. the potential to give energy back again. As it falls and gains 1, 2, 3, 4, 5 units of kinetic energy, it gains or loses, depending on which verb you want to use, negative 1, 2, 3, 4, 5 units of potential energy. The numbers add up to 0. If you define it to be 0 or pi or any number, I don't really care what you define it to be up here, but let's call it 0, all right? It stays 0. It's a conservative process. In a similar way, today's dark energy and the inflaton, which we think inflated the universe, it had a gravitationally attractive component because it had a positive energy density, and anything with a positive energy density has an attractive component, all right? The anti-gravity is caused in relativity by what's called negative pressure. That's what causes the anti-gravity effect. And for that, I can't really give you an easy analogy. But go back to the gravitating component. Because the dark energy has an energy density, there's a gravitationally attractive component, and hence a negative gravitational potential energy associated with it. That negative gravitational potential energy exactly balances the amount of positive energy added to this growing universe, both during the inflation stages and now. Pretty nifty, huh? So each of you consists of stuff which 13.8 billion years ago, in the first 10 trillionths of a trillionth of a trillionth of a second, was the dark energy of back then. We call it the inflaton, the thing that inflated the universe. And it then decayed into more or less normal stuff, which then somehow got a baryon asymmetry, which then ultimately led to us. So each of you contributed to the bang of the Big Bang, because inflation was, in my opinion, and that of a number of physicists, the bang of the Big Bang. Yes, there was a little bit of stuff before that. You could say that that was the Big Bang, whatever made it come into existence. But that was only a little bit of stuff, and it didn't have to expand much. Most of the stuff and most of the expansion occurred during the inflationary epoch. And that was driven by stuff which is now us. But we don't have the negative pressure, so that's why this is not continuing. So it conserves energy. You may rest easy, okay? You can sleep peacefully, but that's a great question. Yeah, yes, right there.
Going back to the pie chart,
Yeah.
dark energy, dark matter, no energy, and no matter.
Oh, by the way, just a minute. Stay tuned. I'm going to... But I was wondering where that slide went. So Robert Frost could not have known about cosmology and the possible fate of the universe when he wrote his famous poem in 1923, Fire and Ice. But it's appropriate given what I just talked about. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, Frost would prefer the collapsing universe that ends in fire, a passionate universe. But if the universe and he had to perish twice, then eternal expansion and an ending in ice would be okay with him. And that's perhaps appropriate given his name, Robert Frost. Okay, so going back to, it's not very far away, going back to this pie chart, which I said is what the early universe people had to use to extrapolate and figure out what the current expansion rate is.
Going back to this, right?
Yeah.
Is it knowing that we know as little about 95% of the makeup of the universe, if you will, is it possible that those ratios are slowly changing over time?
Oh yeah. Are the ratios changing over time? Indeed they are. We know they are because of the following. The whole pie is the density of the universe from all of its components, it has to add up to 100% of the pi. Unless we're missing something, as we were back when I was a student. But let's assume we're not missing anything. The whole thing has to add up to the whole pi, okay? But the normal matter and dark matter are being diluted away by the expansion of the universe. Think about a box with 1,000 particles in it. As the box expands, the density goes down. So in the context of this pi, that means its slice goes down. The dark energy, if it's the cosmological constant or nearly the same as the cosmological constant, its density does not change. Contrast that with the density of matter, which is going down. So its relative contribution is going up, the dark energy. 13.5 billion years ago, the dark energy sector was infinitesimal. In a few tens of billions of years, the ordinary and dark matter will be infinitesimal. And our universe will be not just accelerating its expansion, but exponentiating, like an inflationary universe, because there won't be the normal matter and the dark matter trying to some degree, resist the exponential expansion. So, in fact, the dark energy will become dominant, and that's why I said look at a galaxy pretty soon through a telescope, because in a few tens or hundreds of billions of years, there won't be any galaxies to see, because the dark energy will have become so dominant in the universe that it'll whisk all those other galaxies away. Pretty cool, huh? Yeah. Yes, right there.
How is it that one Big Bang wasn't just a super massive black hole?
So what was the Big Bang? A supermassive black hole? Probably not. It was probably something from nothing, either in a bigger hyperspace or as a result of a quantum fluctuation in energy of a universe that already existed. Every bit of space is continually going through quantum fluctuations in energy. And you can achieve, in some cases, we think, conditions that lead to this inflaton, this stuff that has a negative pressure that inflates the universe. Indeed, if you subscribe to the inflationary idea for the early expansion of the universe, you come to the conclusion that indeed a multiplicity of universes does exist. That's why I said that multiplicity of universes coming out of Einstein's pipe was only partly a joke. More and more serious card-carrying physicists are coming to the conclusion, and this is sort of an extension of the Copernican principle yet again, that ours is not the only universe. The multiverse, that's right. But though that conclusion comes from scientific reasoning and things that we think we know, by its very nature, that conclusion is at the boundary of what we can call rigorous science, because right now we do not know of a general way to test for these other universes. If they collide, then it turns out you can tell. But if they don't collide, how do you test that hypothesis? And that's why it's at the boundary. But it's not science. Some types of physicists say that that's not science. No, I disagree. It's not that we got up at 3 in the morning to go to the bathroom and said, well, let there be a multiverse. Wouldn't that be cool? There are good reasons for thinking, many reasons. I gave inflation, chaotic eternal inflation. Andre Linde at Stanford is championing that, and it makes a lot of sense to me. Or quantum fluctuations in some pre-existing hyperspace that just produce little soap bubbles. Those could be other universes as well. But there are many ways you can produce multiple universes. Now, the black hole you're thinking of, Alan Guth at MIT has written papers on how if you could create a black hole in your laboratory, the simple equation suggests that that opens up to another universe on the other side of the black hole. But there are probably problems with that. But I know where you're coming from. It has been postulated that our universe or other universes could be born from black holes, basically. But probably they're not. But inflation and stuff, probably yes. And you had a question here.
Yes, is it possible that the speed of light evolved and is not constant?
The question is it possible that the speed of light evolved and is not constant? And that could be messing us up into thinking that the universe is accelerating. Indeed, some people thought that that might be the explanation. But now there are a number of measurements that all give the same result, and some of them don't depend on what the speed of light is. So I think the accelerating universe is okay. Nevertheless, it's an interesting question. Could the speed of light have evolved? We think it probably has not, because we measure certain combinations of fundamental quantities, and those combinations turn out to be even more fundamental. There's one, for example, called the fine structure constant, which dictates the energy levels in atoms, of the electrons in atoms. And it's the charge of an electron squared over basically Planck's constant divided by 2 pi, but who cares, divided by c. So E squared over h bar c. And we can tell by looking at spectral lines from galaxies billions of years ago that the fine structure constant was the same back then as it is now. So that either means that neither E nor h bar nor c are changing, or that they're all changing in such a way as to keep the combination the same. That's probably not the case. Plus, there are other combinations, and you can make other such arguments. And theorists are painted into a very tight corner if they keep on insisting that these parameters change. So probably not. Now, very early in the history of the universe, these things like the fine structure constant and other constants associated with the strong nuclear force and the weak nuclear force, fine structure constant is associated with electromagnetism, they are what's called the coupling constants. And in unified theories, in string theories in particular, in the very early universe, they were the same, and they changed pretty rapidly into essentially today's values. So very early on, yes, they may well have changed, but that's in the first fraction of a second of the universe's existence. And it's theoretical work which does not then say that, well, another necessary consequence of this would be that currently these things are changing. No, currently they are not changing. There were specific reasons that they changed long, long ago. Okay? But interesting question. Cool. Yes?
Do we know how dark energy is multiplying?
Do we know how dark energy is multiplying? We think that it's multiplying exactly in proportion to the expansion of space. That is, you double the volume, you have double the dark energy. But that would be the case if it truly is Einstein's cosmological constant. The data are consistent with that, but the error bars are still big enough to admit other possibilities, okay? So we don't know for sure that it is multiplying in proportion to the volume of space. But the data are certainly consistent with that option. And, it's the option that corresponds to this just being the vacuum energy. And then you ask, why would it be that number? The number you calculate is infinity. But no one believes in that infinity. And there are other infinities you get in quantum mechanics. And we sweep them under the rug through well-defined processes. So you sweep that under the rug, and then you calculate that the vacuum energy should be only 10 to the 122nd power. I kid you not. A googol spelled G-O-O-G-O-L is 10 to the 100 power. That's a very big number. It's a huge number. This is 22 orders of magnitude even bigger than a googol. 42 orders of magnitude bigger than the number of particles of all types, including photons, within the observable universe. There's only about 10 to the 80th particles of all types within the observable universe. So the vacuum energy should be enormous. It's not. It's either 0 or it's what we measured, 0.7. Okay? If what we measured is some other dark energy, then it could still be that the vacuum energy is 0. But let's assume that what we measured really is the vacuum energy. How do you get 0.7? Physicists would say, okay, we don't know how to get 0, but we can imagine a perfect cancellation, not like the baryon asymmetry, that somehow And in string theory, they talk about bosonic vibrations and fermionic vibrations and all kinds of yada yada. Maybe there's some way that they all cancel each other out and you get zero. Not that they figured out a way to do that, right, Shannon? But they think maybe there could be a way to do that. But to have a cancellation that's not quite perfect at the level of basically 1 out of 10 to the 122, how do you do that? At least the baryon asymmetry is only a part in a billion. That is enough of a problem. But how do you get a cancellation that's perfect to a part in 10 to the 122nd? That's one reason a lot of theorists don't like the possibility that this is the vacuum energy. And that's why they argue that it's some sort of other dark energy. But the data are homing in on a vacuum energy. So if it is a vacuum energy, how do you reconcile that? Simple, in principle. Suppose there's a multiverse, and some numbers have no fundamental reason behind them. They just are. Just like Earth has no fundamental reason that it has the mass that it has and the distance from the sun and the atmosphere, blah, blah, blah. The ancient Greek philosopher could have thought until they're blue in the face, what is it about fundamental physics that makes Earth this good for the development of complexity culminating in life? There isn't anything special about Earth. In an ensemble of planets, you'll get some where conditions are conducive to the formation and evolution of life, if life is a natural process. And we, if life is to exist, obviously live in one of the good ones. We'll take this a step further. If the universe's dark energy, vacuum energy, were big, it would fly apart so quickly that no stars and galaxies would ever have formed. We wouldn't be here. Steven Weinberg, Nobel winning physicist in the 1980s, made this argument. He said the cosmological constant can't be bigger than about 10 or 100. I forgot what he said, something like that. Because if it were, out of all the numbers it could be, if it were bigger than 10 or 100, we wouldn't be here. So he said it's got to be a small number and, possibly zero. But out of the continuum of numbers, what are the odds that it's zero if there's nothing special that dictates it? Out of the continuum of numbers, the odds are that it's not zero. But it can't be big. Otherwise, we wouldn't be here. So we expect, through this anthropic reasoning, right, we exist, therefore what conclusions can we draw? This is a little bit shaky. It's not certainly mathematically logical, but it's a plausibility argument. We expect to live in a universe with a small but not precisely zero vacuum energy. And there's an ensemble, there's a cosmic archipelago of universes out there, spanning all possible vacuum energies, because there is no reason that it has to be any particular way. It's just one of the constants of nature. And there are others as well. The mass ratio of the proton and neutron, a boring thing. They're nearly the same mass. A neutron is 2 electrons more massive than a proton. Not much. You play with the equations of physics. If that mass ratio were any different by just a small amount, you're in most cases led to a boring universe, a stillborn universe. You don't even have the rich periodic table. You have only helium or only iron or only hydrogen. You don't have a rich periodic table. You don't have carbon with its long chains, blah, blah, blah. And all I did was fiddled a little tiny bit with the mass ratio of the neutron to the proton. So there are several quantities like this. Martin Rees, very famous astronomer in England, has written a book called Just 6 Numbers. And he explores what would the universe be like if you just altered those numbers ever so slightly. He's not even altering the laws of physics, just alter boring numbers. And in most cases, you end up with really boring universes. So if there is only one universe, why is it such an interesting one that led to complexity? You might say, what better evidence do you need for a supernatural creator that made it this way by design? I can't refute that argument. but nor can I take it anywhere from a scientific perspective. I can use science neither to prove nor to disprove the existence of God. So that might be the correct answer. But if I want to approach it from a scientific perspective, I'm then left with one universe that was this way by chance. I just don't buy it. Or a multiplicity of universes where at least some of them are good. Well, that sounds real fine to me, especially since we have theories like inflation, which already tell us that there's likely to be a multiplicity of universes. And symmetry breaking and all these things that theorists talk about may well occur in different ways. It's like I spin a coin. This is the analogy I give to my class. I spin a quarter, and it's spinning. It's unified. It's symmetric. But then it loses energy due to friction, and it lands heads or tails, and it might land over there or over here. Those are all, in a sense, different universes. They look slightly different. So, fundamental physics is now claiming that the multiverse idea may well be correct. And anthropic reasoning takes you in the same direction and has a number of historical precedents, like the Earth analogy I gave. So I'm a big believer, I don't like to use that word, but I like the idea of a multiverse for these couple of, so one there and then probably we need to halt. Yeah, okay.
Yeah, what about interdimensional universes?
Interdimensional universes, yeah. If these things are, soap bubbles flying around here, then we're like membranes, brains, they're called, B-R-A-N-E-S, in a higher dimensional bulk. The brain world string theorists are talking about this kind of thing now. And there could be a parallel universe 1 millimeter from your nose and you don't see it because it's in a different dimension. It's possible. It's also possible, as Elon Musk has been talking about recently, that we're some advanced alien teenager's video game, right? So, do I really think there's another universe a millimeter away from me? No, but it could be. And do I think we're an alien's video game? Well, maybe. It's an attractive argument. Last question right there. Is that Maggie back there? No, okay, sorry. Multiverse. Yeah, what's the definition of that universe, the multiverse? This reminds me of a joke, a nerd joke. When I was a kid, the joke was, define universe and give 3 examples, right? Because it was the universe, right? There's one. That's what you mean by universe. There's only one. It's a joke now because we're seriously considering these separate things. So what we mean by them is that they are what we call causally disconnected. In other words, what happens in one universe doesn't really affect another, although even that might not be the case, because some people have speculated that gravitons, the carriers of gravity, actually can go from one membrane to another. So that might be one way to test for their existence, by the way. But basically they're regions, they're separate regions of space that are not just, places that are too far for us to see, but we're part of the same inflating domain. They are other places, I'm being a little bit hand-wavy here because the actual definition becomes quite technical and mathematical, and there are actually level 1 universes and level 2, level 3, level 4. Max Tegmark at MIT has a paper on that. There are different things. The simplest case is one that I actually didn't even include, but the universe that inflated is much, much bigger than the distance to which we can see. So our observable universe is a subset of the whole universe. But many physicists say, well, volumes out there where there are aliens that can only look out, 10 billion light years or 12 billion or 20 billion or whatever, there's their volume, and here's our volume, and here's someone else's volume. Even those are different universes according to some physicists, although Tegmark would say that's a level 1 multiverse. In those universes, you basically have the same laws of physics because it came from the same inflating domain. But you could imagine different inflating domains, or you've got a universe where a quantum fluctuation occurs and it sprouts off another universe like a branch of a tree. And then that branch has branches budding off. This is a chaotic, eternal universe. Eternal inflation, it's called, by Andre Linde at Stanford. So in that case, there never was a beginning and there never will be an end in the multiverse. But anyway, there's no clear definition by what we mean unless you get quite technical mathematically about what you're talking about. But you can just kind of think of a bigger hyperspace. Think of this room as being some hyperspace. And you've got a soap bubble here, that's our soap bubble, and here's another soap bubble that just formed independently. Here's another one, right? Just make a bunch of soap bubbles in this room. And think of them as being universes that have no physical contact with one another. That's what we mean when we talk about multiverses. Budding off or soap bubbles in a room.
Would it be fair to say the laws of one universe don't apply to...
So yeah, it might even be the case that the laws of one don't apply to the laws of the other, because when I was a graduate student, string theorists said, we're so smart, we're going to figure out the one way God could have created the universe, because there's only one mathematically and physically self-consistent way you can have a universe. Well, here we are 30, 35 years later, and the string theorists are saying, you know what? There's a landscape, that's the term they use, of 10 to the 500 power types of universes. And it's how you take these multi-dimensional spaces, 11-dimensional spaces, and most of the dimensions are small, and they can have different mathematical shapes called Calabi-Yau spaces and weird things like that. And there are 10 to the 500 power possibilities. So the string theorists now are among the greatest proponents of the multiverse theory, and depending on exactly how many little dimensions and big dimensions and all that there are, and depending on what the shape of the little dimensions is, the laws of physics may well have a different mathematical form in these other universes. And that's what I think Tegmark calls either level 3 or level 4 universes. So I think we'd better start. You've been a great audience. But,
that was a very thorough discussion. It all started here?
It all started here.
All right. I'm really proud of that.
Are we taking away from nighttime observing, or is it still cloudy?
Well, that was my next announcement. We had intended to open both the 60-inch and 100-inch telescopes. It doesn't look good. They are open for you to look at, maybe not through, but we have docents and operators in both of the domes. We have some personal telescopes from Los Angeles Astronomical Society. I don't think they're going to get any better than we are. But thank you all for attending. This was a great event. Thank you, Alex.
Thank you.